Here we have a circular disc of mass m. Now it's a uniform lamina, so we can ignore its thickness. Its density is the same everywhere. We want to find its moment of inertia about an axis, perpendicular axis passing through the center of the disc. Now for our mass elements in this example, we take circular rings centered at O. So here is one such ring. Its width is delta r, and of course we will let that go to 0, so we will get a mass element. So again, it's obviously not a point mass, but the calculations will still work out. The distance of the ring to the axis of rotation is r. So delta r is the change in r in this case. So we're not dealing with x and y coordinates here. It's easier just to exploit circular symmetry here. So the thickness of, or the width of a ring is not delta x or delta y, it's delta r, is the change in r. Now we need to get the mass of this ring. To get the mass of the ring, we need its area. So again, we forget about the thickness. We assume the thickness is negligible. So we will need the mass per unit area, rho, here. So rho is not really a density, it's the mass of 1 meter squared rather than 1 meter cubed. But we can multiply that constant by the area of this ring to get the mass of it. So here's a rough sketch of our ring, a plan view if we look down on it. And how do we get the area? Well, this distance here is r, and the width of it is the change in r, which is delta r. So what we do is imagine opening this out. We make a cut directly across it like this and open out what we get, and if we could do that, we would get approximately a rectangle of width delta r. So delta r is this distance here. And what about the length? Well, if we open this out, we need to know what is the distance all around a circle. If we start here and go all around a circle of radius r, well, that's the circumference of a circle of radius r, which is 2 pi r. So the length of the rectangle is approximately 2 pi r. Of course, the outer length is a little bit more because we have a circle of larger radius, a circle of radius r plus delta r. But if delta r is very small, then both sides of this shape will be the same. So the bottom side is 2 pi r, and the top side will also be approximately 2 pi r, depending on how small this is. In the limit as this goes to 0, of course, we will have a rectangle. Well, what's the area of the rectangle? Well, that's easy. We just multiply the two sides together. 2 pi r by delta r. So we could call that delta A, if you like, for area, the area of this mass element. And the mass of it, delta m, is delta A times rho, the area times the mass per unit area. So that's going to be 2 pi rho r delta r. So there it is, there's the mass of the element. So how do we get the moment of inertia of this ring? Well, we must multiply the mass of the element by the square of the distance from the axis of rotation. So we multiply it by r squared. So we get an r cubed in this. So we must do this for all rings centered at 0, centered at the axis of rotation, centered here. And we must sum all the moments of inertia if we want the moment of inertia of the entire disk. So we sum from r equals 0 to r equals a. So the innermost ring is just a little dot at a, at the origin, if you like, and we sum all the elements for all the rings until we get to the outermost ring, which is at the edge of the disk. Okay, so since this is just an approximation to the moment of inertia of the disk, we have to let delta r go to 0 to make that approximation exact. So all the rings become effectively rectangles whose areas are 2 pi r rho delta r. So this is only an approximation, so we make that approximation exact by taking this limit, and the limit of a sum is the integral from 0 to a. So we have 2 pi r cubed rho in here, and we replace delta r with dr. So in the limit as delta r goes to 0, this is dr. So we integrate this with respect to r. The 2 pi rho are just constants. So if we integrate r cubed, we get 1/4 r to the power of 4. The upper limit is a, so we plug in a. Lower limit gives us 0. Now let's get I in terms of the mass of the disk. Well, since the disk is a circle, of course, the area of it is pi times the radius squared. So we're taking the radius to be a, so that's the area of the disk, and we multiply that by the mass per unit area, which is rho. So we're going to get rho pi a squared for the mass of the disk. We call that mass big M. And again, this makes sense from the point of view of units. Rho is mass per unit area, kilograms per meter squared, and this thing here has units of meters squared. So these cancel out to give us the correct units of kilograms. So that's M, and we want to express I in terms of M and A. So we need to somehow factor this thing out of this expression here. We've rho pi a to the 4 here. If we take rho pi a squared out, if we take rho pi a squared out of this, we're left with a squared over 2. So we have ma squared over 2.